Great. So hopefully you had a chance to try the warm-up problem. Again, I've got a differential equation because I've got a derivative and an equal sign, and this is pure time because the only variable that appears on the right-hand side is our independent variable, or the one that's in the denominator of our derivative. So to find the antiderivative, or rather to solve for y of t, it means we're going to find the antiderivative. Now, I haven't exactly written the notation this way usually, but I'm going to because of where we're headed today. Normally, we're finding an antiderivative by taking an integral. And just for the sake of like mathematical completeness, what I'm actually going to do here first is multiply both sides of the equation by dt. Now, when I do that on the left-hand side, those dt's cancel. And on the right-hand side, I'm still going to have that dt. Well, what that's allowing me to do is to now swoop in with an integral on both sides. So if I rewrite that, the left-hand side now says the integral of dy is equal to the integral of t squared times 3 minus t cubed dt. Now, there are a couple of things that I want to point out. First of all, there's an invisible function in here. And when there is no function to write, that invisible function is a 1. The other thing of note is that notation-wise, this integral is saying, take whatever's between the integral symbol and my d something and find its antiderivative. So I'm ready to find that antiderivative of both sides. On the left-hand side, if I integrate 1 with respect to y, I get y. Now, technically, I get y plus a constant. But if we had a constant on both sides, we could just smush those together into a single constant. So by convention, we're going to smush those together into a single constant on the right-hand side. Speaking of the right-hand side, we have two choices for how to evaluate this integral. We can either do this as a u substitution, or we can distribute the t squared out. I'm going to vote for distributing it out, but if you did a u sub, that's totally fine. When I distribute this through, I'll have 3t squared minus t to the 5th dt. Now I'm ready to get that antiderivative going. So the antiderivative of 3t squared, I'll get t cubed. This, I'm going to add 1 to that exponent, get t to the 6th all over 6 plus a constant. Here's where my initial condition comes in. And I know it's a little bit awkward, but we tend to refer this as an initial condition or an initial value problem, even when neither of the numbers are 0. That's just kind of a mathematical convention of how we refer to it. But this notation tells me that when t equals 1, y equals 2. And I'm going to plug those in down here to solve for that constant of c. So I'm going to put in 2 for y and 1 for t. 1 cubed is 1. 1 to the 6th is also 1. So I'm going to have 1/6 plus a constant. So to solve for that c, I'm going to add, well, let me do this as subtracting the 1. So I'll be at a 1 and then adding 1/6. So I think I'm going to get 7/6 is equal to c. So my final answer in terms of finding y as a function of t, that final answer would look like this entire thing, but where I've plugged in the value for c. So t cubed minus t to the 6th over 6 plus 7/6. And that would be my final answer. Okay, I don't actually think that it's super important that you have all the vocabulary down, but recognizing the type of differential equation it is does help us to know how to solve it. And I guess I should give us some instructions here. So we are looking to solve this. So let's talk for a second about vocabulary. This is first order. because I've just got a dy dx, this is non-autonomous if we're giving vocabulary from our textbook. Now, all that really means is that when I look at my derivative piece, whatever variable is on top, that's my dependent variable. And whatever variable is on the bottom, that's my independent variable. When I look over here on the right-hand side, I have both of them. I have both the independent variable and the dependent variable, which makes this non-autonomous. If I covered up the x squared, this is now considered an autonomous differential equation because it only involves the letter in the letter on top of my derivative. If I covered up the y, it would be a pure time differential because it only involves the letter in the bottom. But as it stands, this thing is non-autonomous. And at this point, the only method that we have that we hope is going to work is this idea of integration. So what I'm going to do is the same sort of process that I did on that warm-up problem. And I'm going to start by multiplying both sides by dx. Well, when I do that, and I've got that dx times dy dx and x squared y times dx, over here my dx's cancel out. But if right now I were to go ahead and put integration symbols, I'd have a problem because on the right-hand side, that dx is telling me I'm expecting to find the antiderivative of something with x's in it, not this pesky y. So before I can apply that integration to both sides, I need to get that y to the other side of the equation. And I'm going to do that with division. So I'm going to divide both sides by y and then clean this up a little bit. So on this side, I've got 1 over y dy. And on this side, because my y is canceled out, I've got x squared dx. Now I'm ready to integrate both sides. Well, when I integrate the left-hand side, the integral of 1 over y dy is going to lead me to natural log of y. And on the right-hand side, when I integrate this, I'll get 1/3 x cubed plus a constant. Now, there's an extra thing that I would do here that we didn't really have to do in the previous problem. If the question asked us to find y of x, well, we still have a little bit of work to do because right now that y is trapped inside of a natural log. So if I were to actually want to solve this to make it say y of x, I'm going to rewrite that to say y equals e to the 1/3 x cubed plus a constant. I'm going to pause there for a second because I'm about to do some algebra tricks, but I wanted to see if there are questions about getting that far. Scanning for questions. Not seeing questions. Okay, so now let's do a couple of algebra tricks. We don't have to do these, but I'm just going to show you. So this is kind of mathematical convention of what we would do from there. One of the things that I haven't taken into account is the fact that that y was inside of an absolute value. We didn't really do anything with that absolute value piece of it, but we can correct for that if we do some algebra over here. If I had something like 2 to the 3 plus 5, that is certainly 2 to the 8th, but it was also 2 cubed times 2 to the 5th. And it's this version of that same idea that I want to apply down here. So right now, I've got e to the 1/3 of x cubed plus a constant. but I'm going to choose to rewrite that as e to the 1/3 of x cubed times e to a constant. And then in my last step, I'm going to say, wait, e raised to some constant is some new constant. Because if I plugged in e to the 6th into my calculator, or e to the 47.9, or e to the 1.38, it's going to spit out a number for me. So by convention, we would take this and choose to rewrite it as c e to the 1/3 x cubed. Now, I've used the same letter there, and I really shouldn't because they're not the same constant. So I'm going to switch that one to be an A. The textbook uses subscripts, so it would like call that C1 and C1 and then switch it around to a C. But now we've taken into account the fact that the y might need to be positive or negative depending on what our initial condition is, because that value of A could now take on either a positive or negative value. Okay, so I know there's a question in the chat in terms of we're only going to do this separation stuff for non-autonomous. I want to address that question head on, because I would say I'm going to separate the variables. I'm going to use this separation of variables technique anytime it's autonomous or pure time or separable. Let me do this example and then loop back around to what I mean by that. Okay, so I'm walking up to this differential equation. It is non-autonomous, and it's not a pure time differential because I've got both x's and t's in here. So I'm hoping that it's separable, which it is. To show that it's separable and to separate those variables, I'm going to start by multiplying both sides by dt. So they cancel out over here. So now I've got dx is equal to secant of x divided by t squared dt. And then I look at that and I say, wait, I can't quite do my integration yet because I've still got x's over here on the right-hand side. So I'm going to divide both sides by secant of x. So I'll have 1 over secant of x dx is equal to 1 over t squared dt. Now I've separated my variables, I've got all the x's on one side, all the t's on the other, and I'm ready to integrate. Should I let you all try that on your own? So if I take a look at the left-hand side, personally, I don't love trig. Actually, that's not true. Trig's fine. But I would much rather look at things in terms of sines and cosines. So I'm going to take that 1 over secant and say, oh, wait, that's just cosine. And on the right-hand side, before I take the antiderivative, I'll go ahead and rewrite that as t to the -2. Now I'm set up for my antiderivatives. So the function whose derivative is cosine, that's going to be sine. And over here on the right-hand side, when I add 1 to the exponent, I'll have t to the -1. And dividing by -1 just makes it negative. So I'll have negative t to the -1. And don't forget that plus a constant. I wasn't super specific here, but let's say that I wanted to solve this for x of t. Then to get the x by itself, I'd have to do inverse sine. So it wouldn't be pretty, but I could say the x of t was equal to sine inverse of, we can leave it like this or write it as -1 over t plus a constant. Questions on this one? Totally. So there are a ton of questions coming up about that sine inverse thing. So if I told you that, well, let's just put it this way. I'll use real numbers. So if I told you that sine of pi over 2 was equal to, well, here's the part, you should know the value, but I'll just put it in here for us. Sine of pi over 2 is equal to 1. I could also write this statement as pi over 2 is equal to sine inverse of 1. So this is, sine is just, sine inverse is the inverse function of sine. So if I'm trying to get the thing out of the sine, I apply sine inverse to it. It's kind of like if I had, well, with e and natural log, those are inverse functions. So if I had natural log of, I don't know, 4 is equal to x, I could also write this as saying 4 is equal to e to the x. And the reason that works is because e to the x is the inverse function of ln. When it comes to sine and cosine and tangent, we just write it as sine and then with a little power of -1, but really we mean sine inverse. It doesn't mean 1 over sine. I'm hoping that helped. Cool. So, oh, and by the way, if you're typing this into WebWork, I didn't see any problems where you would need it yet, but I haven't looked at homework 6. But WebWork will also, you can just type that in as sine little caret -1 in parentheses, and it'll know what you mean. Okay. So I want to back up and answer a question that popped up a minute ago of when are we using this technique really? Of separating and then integrating. Technically, we have been using this technique since section 4.6. In section 4.6, every differential equation we encountered was a pure time differential. So we didn't really have to do it because everything in section 4.6 was written more in the form like y prime equals, I don't know, let's say x squared plus 4. And then we looked at that and we said, well, how do we undo the y prime? We take the antiderivative. So we could just write that as y equals the integral of x squared plus 4 dx. Or we could just straight up find the antiderivative and go straight from there to y equals 1/3 x cubed plus 4x plus some constant. And all of this was fine, and all of this is still fine. But if you want to sprinkle on sort of what's happening math-wise in the background, well, what's happening in the background here is that this y prime is dy dx. And we could multiply both sides by dx to get the differential dy is equal to x squared plus 4 dx. And then we can integrate both sides of that differential. Recognizing that there's an invisible function here of a 1. So when we integrate that with respect to y, we just get y. So technically, we could have been doing this all along. But for a pure time differential equation, it's not really needed because we already have this form where we're looking at this and saying, oh, well, this only has x's in it. We're just finding the antiderivative. Well, where things get more interesting is when we have either autonomous or non-pure time differentials. Okay, so I'm looking at this thing and I walk up to it and I say, hey, it's autonomous, because that variable that's in the numerator is the only variable that appears over here. Since it's autonomous, I know that it's also separable. But to separate it, I have to remember that I don't get a choice of which side of the equation the y's end up on and which side the t's end up on. And that's because my first step here is going to be to multiply both sides by dt to get it out of the denominator. But once I do that on the right-hand side, you'll notice my y's are in the wrong place. I got y's over here, but my dy is on the left-hand side. So I'd have to divide the entire thing by y plus 1 squared in order to actually separate those variables. So on the left-hand side, I've got 1 over y plus 1 squared dy. And on the right-hand side, this time I've just got that dt term. But now I can integrate both sides. And in the interest of time, I'll do this one for us. But looking at that, I'm thinking about a u sub on the left-hand side because of that y plus 1 in the denominator. If you can do this u substitution in your head, great. I'm going to actually write it out. So to do the u substitution on this side, and I'm worried I'm going to run out of space, so I'll just bring it up here. 1 over y plus 1 squared dy. I'm going to let that y plus 1 be equal to u, which means my du is dy. And I can rewrite that to say 1 over u du. Integrating this, I'm going to end up with, oh wait, sorry, it's not 1 over u, it's 1 over u squared. That would have been a big mistake. So I missed that too. Now, before I integrate that, I'll rewrite that as u to the negative 2. Find my antiderivative, u to the negative 1 divided by negative 1, or negative 1 over u, which then becomes negative 1 over y plus 1. So that is the answer to my antiderivative on the left-hand side. On the right-hand side, when we integrate dt, we're again going to remember that there's an invisible 1 in there. So when I integrate with respect to time, I will get t and then plus a constant. Here, depending on what our instructions said, right? Let's say that we needed to solve for y of t. Now I've got to do some algebra to rearrange and get the y by itself. Would anyone like to watch me do the algebra to get the y by itself? I got some yeses. So let's go ahead and go through the algebra to get the y by itself. I'm going to erase my u substitution just to give myself more space to work on the algebra. Going once, going twice. Take a screenshot if you want it. So to get that y by itself, let me go ahead and rewrite it over here. So I've got negative 1 divided by y plus 1 equals t plus c. Personally, if I've got fractions, I just multiply both sides by whatever gets rid of the fraction. That's what I do when I've got a dy dt. That's what I do when I'm doing algebra. So I'm going to multiply both sides by y plus 1. So over here, those y plus 1s would cancel out, and I've got negative 1 is equal to t plus c times y plus 1. So I can divide by the t plus c and get negative 1 over t plus c is equal to y plus 1. And then y of t would be equal to negative 1 over t plus c minus 1. There are other ways that we can rearrange it, but they'll all be algebraically equivalent. So I think that's our fastest path to get the y by itself. Pausing just for a second. I've got time to squeeze in one more example of this, I think. And then I'll switch gears and talk a little bit about some of the web work problems. Oh, excellent question. So folks, there was a question in the chat about solving for C. I didn't actually give us an initial condition to solve for C. How about if I give us an initial condition on the next one? Okay, this is a differential equation because I have a derivative and an equal sign. I've got y's and t's in the mix, so it is not pure time and it is not autonomous. So if we've been asked to solve it in the context of 17b so far, it better be separable. Well, my first step in trying to identify how it's separable, I'm going to start by rewriting that y prime as dy dt. So I've got y squared times dy dt is equal to t plus 3 over y. Once I've got this here, I'm going to go ahead and multiply both sides by dt because that's going to tell me my t's have to be on the right-hand side and my y's have to be on the left-hand side. So I'm at y squared dy. That side looks good. It looks like it's ready to integrate. And over here, I've got t plus 3 over y dt. This side's still a problem because of that y in the denominator. So I'm going to multiply both sides by y. So here my y's will cancel out. And over here, I can write that as y cubed dy is equal to t plus 3 dt. And I just realized I said I was going to give us an initial condition. So let me make up an initial condition really quick. Let's say y of 2 is equal to 0. Let's see what happens. So I am ready now that I've got my y's separated from my t's. I can take the antiderivative of both sides. So I'll get 1/4 y to the 4th. And over here, that's a 1/2 t squared plus 3t plus a constant. We have a choice. If I'm going to solve for y of t, I can either do the algebra now to get the y by itself, or I can solve for the c first. It won't matter. Sometimes the algebra feels a little bit easier one way. Sometimes it feels better the other way. The other question in the chat here is about the plus c. It doesn't actually matter which side of the equation you put it on, but you should only put it on one side of the equation. By convention, we put it on the right. There's really no rhyme or reason to that. It's just some probably old dead white guy mathematician decided we should put it on the right-hand side. So that's what we do. Okay. So notation wise, this tells me that when t equals 2, y should be equal to 0. I'm going to go ahead and solve for c first, and then we'll rearrange to get the y by itself. So if I do this, when I plug in 0 for y, and then 2 for t, so 2 squared is 4, 4 times 1/2 is 2, and 3 times 2 is 6. So it looks like c is going to have to be -8, which means my equation would look like 1/4 y to the 4th is equal to 1/2 t squared plus 3t minus 8. Then, if I'm going to get the y by itself, personally, I got fractions. I'm multiplying by whatever gets rid of those fractions. In this case, 4. So if I multiply the entire thing by 4, I've got y to the 4th 4 times a half will give me 2. 4 times 3 will give me 12. And 4 times -8, I'm at -24. Then last step, to get that y by itself, I will take the 4th root. Pro tip in terms of typing things into web work. In web work, I would write that in as all that stuff raised to the 1/4 power. Okay, I didn't quite make my 1040 target, but I do think that we've got time. I don't know where that 24 came from, because apparently I can't do arithmetic today. 4 times 8, fun fact, 32. Thank you, Tara, for helping us out. 32. Good times. The web work problems, you know, we've got some ugly shape that looks like this. And one of the questions is asking you to spin this around the x-axis. And another one of the questions asks you to spin it around the y-axis. And we didn't really talk about spinning around the y-axis, and you didn't really do much in lecture with this either. So when we're spinning around the y-axis, our cross section is going to be horizontal. Well, what that means in terms of the equation is we know that when we spin this around, the volume is supposed to look like pi r squared times some sort of d something. But because we're spinning around the y-axis, it's a dy. And because it's a dy, that means that our radius function, let's say that your equation was y equals 6 over x. Your radius function that you're squaring isn't going to be 6 over x. It's going to be this equation rearranged to say x equals. Now, it just so happens that for this particular function, when you rearrange it, it looks almost exactly the same. You multiply both sides by x, you divide both sides by y, and it ends up looking almost identical. That doesn't happen normally, but it happens for this specific question. Then if my bounds here were like y equals 1 and y equals 1/2, then my integral would go from 1/2 to 1. The other question that I have been getting a lot of questions, the other problem that I've been getting a lot of questions about is problem 6. And let me just pull up mine really quick if WebWork didn't time me out. So to be clear, problem 6 is not asking you to solve any of the differential equations. Problem 6 is asking you to try each of those possible solutions in the differential equations. So I want to do one of those. We did some of these on Monday, or we did at least one of these on Monday, but let me do another one just for clarity. So I'm going to pick one of the differential equations. So my first differential equation on here looks like y double prime plus 8y prime plus 12y equals 0. And I'm just going to take my first potential solution. And for my set of equations, my first potential solution, like my A possible solution, looks like y equals e to the -6x. Is that the one I want to use? I'm going to use it, but this one happens to work. So I don't know if it's more instructive to see one that works or one that doesn't work. I'll do this one and then maybe we'll do another one. So if I'm going to check, is this a solution to this differential equation? I'm going to have to find y double prime to plug in and y prime to plug in. So y prime, e to the negative 6x, I'm going to get negative 6 e to the negative 6x. And I need a y double prime also. Well, negative 6 times negative 6 is positive 36 e to the negative 6x. So to check, is this a solution? I'm now going to take these pieces and plug them in over there. So for y double prime, I'm going to replace that with 36 e to the negative 6x. And then I'm adding that to 8 times y prime, which was negative 6 e to the negative 6x. And I'm adding that to plus 12 times e to the negative 6x. And the question is, when I simplify that side, is it equal to 0? Well, that's a 36 e to the negative 6x, 8 times negative 6. Correct me if I get this wrong. I've got a positive 40, I've got a negative 48, and then a plus 12. I know I ignored the e to the negative 6 part, but I think that works out to be 0. So the question in the chat is, so this is trial and error. I'm going to go with yes. Sorry. So you can decide how much time you want to spend on it. When I looked at the problems, I was able to kind of eliminate a couple of them or sort of group a couple of them. In particular, no matter how many derivatives you take of sine or cosine, numbers aren't magically going to pop out. So when I'm looking at the differential equations, if there are numbers in front of things, that probably doesn't belong to the sine or cosine one. I know that's not super helpful, but okay. Question is, can I actually finish off this volume problem? I would be happy to actually finish off my volume problem. And in case anybody missed it, in lecture, he did say that he won't test you on revolving around the y-axis. So you might need it for, obviously you do need it for this web work problem. You might need it for a worksheet problem down the road or something, but it won't show up on a test. Okay, so if I were going to finish this off, I'm going to go ahead and square the 6 and square the y and rewrite this a little bit. So 6 squared is 36. So I'll go ahead and pop that 36 out in front with my pi. And that y squared, because it's in the denominator, I'll go ahead and rewrite that as y to the negative 2. This guy we've actually integrated a lot today. I'm going to add 1 to the exponent, divide by the new exponent. So I'd get 36 pi, and then I'd have negative 1 over y, and I'd be plugging in 1/2 and 1. And I kind of ran out of space, but I trust that you can plug in the 1 and the 1/2. So the question is, do we treat it the same way as if it were x's? Well, we've kind of been treating it the same way as if it were x's in all of the separable problems that we've done today. Meaning the thing that matters is whatever letter is inside here has to match with our d something before we can find that antiderivative.